Okay. All right. After a quick review on the probability, and let's try to look at what's the difference between the probability and statistics. Okay. If you have learned about the statistics, I think they could be much different from probability. Even though that in statistics we use probability a lot, right? But here's something I think something difference between these two. Okay, for the probability, and you might think that we try to predict the likelihood of future events. Okay. But for the statistics, we usually try to analyze the past event. Okay, there's something different. Right? And if you look at these two subjects from science viewpoint, you might see that the probability may be a theoretical subjects. And statistics could be applied mathematics. Okay, it will use some theorems from probability to a practical problem or the real-world observations. Okay, so these two subjects are inherently different, even though they are related, but it could be different. So in general, for the probability, we will discuss something ideal. And for the statistics, you usually discuss the real applications, okay, real events. And as we mentioned, it could be theory versus practice, okay, for these two subjects. And sometimes we'll say the people who work on the probabilities are optimistic, okay, and for the people who study the or good at the statistics could be pessimistic, okay, because for the scientists in probability, we usually look at the bright side. We'll say, okay, this will happen. Even though there's a chance, we'll say, okay, it will happen. But for the statisticians, they say, okay, according to my study, the chance for something is small. Okay, so in some sense, it will be a little bit pessimistic. Okay, that's just for observations from these two subjects. Okay. So if you gambling with these two kinds of persons, you will see something different. Okay, so this would be the probability versus statistics. But these two subjects are highly related. Okay. All right, so now after we define the events and we now see the compound event. That means we can remember that the event we defined is actually a subset of the possible outcomes. So if we use the viewpoint of sets, we can actually try to produce a new subset with given subsets. Okay, so we might have what we call the compound events. Let's actually try to work on two events using the idea or the concept from the sets, like the intersection or union or the difference, right? If you remember the union of two sets, okay, we might use this idea to define what we call the compound event. Compound event, okay. We might use this. We use the example here for the event A in our supermarket example. At least one supermarket has even number of crayons in use. That be the event A. We can define this event. The other event B would be the total number of crayons in use simultaneously is either 5 or 9. Is either 5 or 9. Okay, so we got these two. Events, A and B. So I use different color. Okay. The event A, I will use the pink background, and for the event B, I use the red later. All right. So you might see the table we just used. We just used in the previous slides, but now it have colors. So the cell with pink background will indicate the event A, belongs to the event A. Okay, so you might see at least one supermarket has even number of crayons in use. We'll count 0 as even number. Okay, so for the pink ones are the belongs to event A, the pink cell, and for the red letters or red digits, it actually belongs to event B. Event B. Okay. So interesting. In our example, you might see the event B is in event A. Okay. The event B is in event A. Okay. Because we have two supermarkets, and the total number of crayons in use for event for event B, we would like to see the total number of crayons in use is 5 or 9. That's odd number. So that means one of the supermarket must have even number of crayons in use. Okay, because the result would be 5. But we add two numbers. The two numbers, the result, if the result is even, is an odd, that means one of it would be even or odd. One of it must be even number, right? So for the event B, will be in the event A. Okay. Okay, or you can just look at these tables. Okay, the red ones indicates event B, and the cell with pink background shows the event A. Okay. All right, so we can do the difference, intersection, or the union. Okay. So if we do the union here, because B is in A, so the union will equal to A, right? Union will be equal to A. And the intersection of these two events will be event B, okay? Because B is totally in, our event B is in event A. No equal sign. Okay. All right. Is that right? Okay. So the intersection of these two will equal to B. And the union would be A, right? If you use the concept of sets, okay? But what's the difference? What's the difference? The difference of two events. That means the outcomes in A, but not in B, right? So A minus B here would be the cells with pink backgrounds, and but no the ones with red color. Okay, that'll be A minus B. That means the outcomes in event A, but not in event B. Yeah. Okay. And this different from B minus A. These two, the result of these two are very different. This indicates the outcomes must be in event A, but not in event B, not in event A. So these two will be very different. Okay. All right, so let's move on to. All right, so after we know the events, here we would like to define the independent of two events. Independent of two events. And remember that for each event, we can associate its own probability, right? For each event, we can give or associate the corresponding probability, like here, right? Okay. So now, if we say these two events are independent, that means we consider their intersection. If two events are dependent, the probability of this, the intersection of these two events will be equal to the probability of event A times probability of event B. Okay, so these two events are independent. Okay. So when we learn probabilities, we would like to see the events are independent. So that'll be easier for us to do the calculation. Okay, to do the computing. Okay, so for probability, we like independent event. So these two events are independent. There could be no any relations. Well, that'll be easier for us to calculate. But for data science or data analysis, we do not like the independence of two events because we would like to see the relation between different events. So for data scientists, we don't like independent events because we would like to see the relation between different events. Okay, so this could be the difference. All right, so this would be the independence, and yeah. This is the reason. Okay. That means because for data analysis, we would like to find out the reason or maybe do the prediction. Okay. So if we can find some other related or dependent events, we might study on that and explain something. But if the events are totally dependent, that means we cannot use that to do the predictions. So in general, when you do the data analysis, you might see you should like dependent events. Okay. All right. So furthermore, we can see what we say the conditional probability. Okay. So that's also considered two events. And we would like to see the probability of event A for, or when we know the probability of event B. Okay, so under the condition that we know the event B. Okay, so it will be defined like this. Okay, I will say that the probability of event A given event B. Okay. So that means we would like to know the likelihood of an event A with some knowledge of the event B. Okay. So this will be the definitions. That means when we know the event B, how about the probability of event A? Okay, so you define it like this: the probability of A given B. Okay, so we consider their intersections because we like to see the likelihood of, or the probability of event A given the condition that the event B occurred. Okay. Okay, so we'll see whether event B will dominate the probability of event A. Okay, so we defined like this. We consider their intersections. There is the probability of intersection of these two events divided by the probability of event B. Okay. Then under these conditions, how about the probability of event A? Okay, so this is why we go like the probability of event A given event B. Okay, so now you can try to derive use the previous examples for these two. Let me see, check these two. Okay. Because I say that B is in A, so yeah, so the probability of event A given event B is the probability of A intersect, the probability of A intersecting with B divided by B. Okay. In our example, A intersect B. The intersection of A and B would be, so that would be is equal to 1. Okay, the very simple one. Okay, right. But how about the P of B given A? Okay. I leave this to you. Okay, you can calculate by yourself. Okay. Okay, and okay, let me see. Get rid of this one. I will erase all of this. All right, so after knowing what the condition probability is, and we might see a very famous one, famous theorem that means that is the Bayes theorem. Bayes theorem. Okay, that's actually based on the conditional probability. Conditional probability. And this, you might see that for this to be meaningful, the events should not be independent. Okay. Okay. This is the reason why we do not like independent events. Okay. Okay, so if two events are independent, so that will equal to, according to the definitions, right? So this will be, that means the probability of event A has nothing to do with the probability of event B. Okay. All right, so but this is for the independence. So if these two are not independent, I mean the dependent, we might consider the Bayes theorem, okay? And it's actually try to reverse the directions. That means if we know the conditional probability of A given B, we might derive the probability of B given A, okay? Using this property, using this property. Okay, so we just we can do this using simple calculation. Okay, simple algebra. We can try to derive this. Okay, so if we try to do some algebra here, this would be A intersect B divided by P of B, right? Okay. What else? Okay, so we can write, if we would like to derive this one using this one, and we can rewrite it like this, but now becomes, right? So you will see what? You will see the intersection, the probability of this, the intersection of these two. Okay. So according to this, we might rewrite this one to be, this one will equal to this times this, right? So that would be P of B given A times P of A divided by P of B. Okay, we can do this reversely. This one equal to this one times this one. Okay. Okay. A little bit confused. Okay, good. All right, rewrite it. But actually, I think I should rewrite it. It will be easier to understand. Is according to this, yeah. So I think the key parts would be the probability of A intersect with B. Right? It equal to this times this, and also equal to this times this. All right. Okay, my job is to get you confused. Okay. Right. So I rewrite it. You can play with that if you're interested. We just do this. Use algebra, okay, simple algebra. So do the calculations. So this would derive the P of right, And this one also gives us P. Right, so these two will be equal. So eventually you will get we just do nothing. We just do the calculation, do the simple algebra. So eventually we'll get this equation. Okay, I think the most important part is this. Okay. Now if you want to derive this, you just move this term to here. Okay, if you want to derive this one, you just remove this term to here. Okay. But this is a very important tool, I think, for data for data analysis. Okay, that's the best theorem. Okay, try to reverse the dependencies. Okay, we might see some examples later in this course. But basically, just remember, I think. The very fundamental definition would be the conditional probability of two events. Okay, and we would like to see two dependent events. Okay. Okay. Hopefully, I'm right. Okay. All right. Now, again, we see the random variable again, and we say that in our case, we would like to see the number of cranes in use simultaneously. Okay, so we could code it like a variables because the number of cranes in use could be a variable, right? That could be a variable, and the value of this random variable depends on the outcomes for the corresponding variables. Okay, so this is why we code it like the random variables. Okay, using our example, the number of cranes in use simultaneously, that's actually a variable, right? It ranges from 0 to 12, 0 to 12. And for each value, it has some associated outcomes, right? Associated outcomes. So this is why we code it like the random variables, okay? And for each value of the random variables, we can define its probability to be the sum of the probability of all the outcomes. Okay. In our example, that means we add the number of cranes in use of two supermarkets up to X. Okay. This is why we have this kind of plot. Okay, as I mentioned. This would be the possible value for our variables, okay? This says the total number, for example, the 5 here says that the total number of cranes in use is 5, okay? And we may have 6 outcomes, okay, that will produce the total number of cranes in use is 5, okay? So we might have the plot like this. This would be the possible value for the random variables, okay? And it associates with the outcomes. So we code it like the random variables. Okay. All right, so sometimes we look at the probabilities. We'll use the frequencies in addition to the probability. Or we might see some frequencies first, then we convert the frequencies to a probability function. Okay. For here, in our example, as I mentioned, if we would like to see how many outcomes that will produce the total number of cranes in use is 5. So we might have 6 outcomes. in our simple space. That means 49, let me go over here, 49 outcomes, okay? There'll be 6 outcomes where the total number of cranes in use is 5. It's 5. Okay. All right, so with different possible value for the variables, it has a corresponding number of outcomes. Okay, that will produce the value. So you might see if the total number of cranes in use is 6, we have 7 outcomes. Okay, that will produce this amount. Okay, so this could be, if we plot it, this will be the frequencies of the variables, the random variables, okay? And according to the frequencies, we may convert the frequencies into probability function, okay? That means we can divide the number of possible outcomes for each value here by the total number of outcomes in the simple space. Okay, that means in our case, that would be 49 outcomes. Okay. So we might convert the frequencies into probability, into a probability. Okay, so in general, for the random variables, we might, firstly, if we just do the observations, we might have the frequencies for the random variables, right? So we might have the plot like this, the plot like this. And the plot here would be, we could say like the density function. And we can, as I mentioned, we can convert this kind of distribution, this kind of density function into a probability function. So if we convert it into a probability function and use this way to plot it, this will be the probability density function. Okay. So after we do the conversions, divide all the possible values here by 49 in our example, the sum of all the possible values, the sum of the probability of the possible value for our random variables will be 1. So you will fit, or you will match the probability, the property of the probability. Okay. All right, so we might see this kind of plots, okay? It could be frequencies, or we can convert it into a probability distribution. All right, so if we just use the frequencies to plot the distribution like this for our random variables, we'll call this kind of graph as the histogram, okay? They just, so sometimes we call the histograms are statistics, okay? Just plot the distribution of the frequencies of all possible value for our random variables. So after we convert it into a probability function for the same distributions, but now we convert the frequencies into probabilities, then we say it would be a probability density function. Okay. So these two, I think they are very similar, and I think we can convert from one to the other. Okay, and they represent the same thing. Okay. So later on, we might see what the histogram is. But here, because we talk about the probabilities, and we will use this if we plot the distribution of the random variables, use this way, we call it like a probability density function. probability density function. Okay, so as I mentioned, the conversion we do from frequencies to probabilities, sometimes we say the process as a normalization to be a probability. Okay, this would be the frequencies divided by the total frequencies. Okay, all right, so this is one possible way to describe the distribution of random variables. We may also use another way to represent the random variables. We can use cumulative density function. This will be probability density function. We count each possible value for our random variables and plot it. Okay. Also, we can use what we say the cumulative density function. For this, we just simply do the cumulative sum for the PDF, okay. That means we start to, let me erase this. Cumulative sums over the PDF, okay. So this will be another way to represent the random variables. It's cumulative sum. Or we say this prefix sum. We just do the summation one by one from first one to the last one and do the cumulative sum. Okay. Okay, so suppose that we have this this kind of series of numbers, integers. We might have the prefix sum, or we say the cumulative sum. We just do the cumulative summation over this series of numbers. So in the very beginning, the prefix sum is 4. Okay, so the second one would be 4 plus 10 would be 14. Okay, just do the cumulative sum or prefix sum. So the next one would be 14 plus 8 would be 22. Okay, the second one would be, the following one would be 28 and 33, okay, etc. So this would be the cumulative sum or prefix sum. Okay, we usually use the prefix sum to indicate the cumulative summation over a series of numbers. Okay, so the same idea would be what we mentioned here would be the cumulative density function that can represent the random variables. Okay, that's simply if you just, I think you can simply work on the PDF and do the cumulative sum from the leftmost one to the rightmost one. Okay, and you do the summation over the frequencies here. Okay, so it's 1 and 3, 6, 10. So it'll be 1, 3, 6, 10. Okay, you just do the accumulative summation over the values here. Okay, from left to the right. Okay, so this is another way we can represent random variables using probability density functions or use the cumulative density function. Both of these approach can represent random variables, and they have the same meaning. Okay, so it depends on what you want to show to the audience. Okay, you can use PDF and you can use CDF. There's no difference of these two, and there's a conversion on these two. I think, yeah, it is what I said here. The PDF and CDF of a random actually they have the same information for the random variables. And this is the conversion between these two kinds of representation. Okay, this is from the cumulative distributions to the probability density function. And this would be from the probability density function to cumulative density function. Okay. All right, so as what I said, these two kinds of representation will have the same information. But it depends on who will see the representation, okay? For this example here, all right, this is actually the number of iPhone sold in each quarter from 2007 to 2013 for each quarter. And the blue ones just the PDF. Okay, the blue one's just the PDF, and the red dots are the cumulative density function for the cell. Okay. Let me explain this a little bit. Okay. Remember that PDF and CDF will have the same information. Okay. So which one to be used, that depends on your objective or depends on the audience. Okay. For this example, you just show the iPhone, the sale of the iPhones. Okay, the number of iPhones sold for each quarter. So from 2007 quarter 3 to 2013 quarter 3. Okay. So you will see the blue ones and the red ones, the blue dots and red dots. Okay. The blue dots here just show the PDF, probability density function. And the red one here shows the cumulative density function. All right, okay. So for these two, I think it has the same meaning. But if you are the boss, you would like to see which curve. Which curve you would like to see if you are the boss? The red one, right? Yes. So next time, if you have some report to your boss, pick up the right one, okay? Even though they have the same information, but I think the red one will make your boss happier, right? Okay. But if your boss has some experience on the data analysis, so it's another story, okay? Anyway. All right, so this just shows that which way you will use depends on your applications, okay? And depends on your the objective of these plots. All right, so this is about the PDF and CDF, okay? All right, so the next part would be the descriptive statistics, okay? And we sometimes use, because we might have a data set or a sample of some data set. It is not easy to describe the whole data set each time, right? So sometimes we need some concise way to describe or to say about some data set, okay? So this is why we have what we call the descriptive statistics, okay? That can help us to quickly have the property of the data set you have. Okay, so this is what we say the descriptive statistics. Okay. All right, so this just try to simplify the way we describe a data set and capture the property of the data set. So we might use the descriptive statistics. Okay, so So let's have a 10 minutes break. Okay, 10 minutes break. All right.